Hoover Dam holds back the Colorado with 3.25 million cubic yards of concrete, 221 meters of engineered mass, completed in 1936. Proof humanity could control water at scale. Then in 1963, a dam that never broke killed nearly 2,000 people in 4 minutes. How we learned to engineer rivers and what it cost when we couldn't begins with stone, mortar, and a problem no one knew how to solve. In May 1887, British Royal Engineer Colonel John Penneycook began building the Mullaperiyar Dam in the Madras Presidency of southern India, attempting to divert the west-flowing Periyar River through a 5-kilometer mountain tunnel into the dry Vaigai Basin. Over 8 years, thousands of manual laborers laid stone block by stone block, completing a structure 53.6 meters high and 365.7 meters long. It was a gravity dam, designed to resist the pressure of 443 million cubic meters of water through sheer weight alone. This masonry approach dictated the physical geometry: a broad base 42.2 meters thick, tapering to a narrow 3.6-meter crest. Workers used local rubble bound with a traditional lime cirque mortar made from lime, sugar, and burnt brick powder. Construction depended entirely on seasonal river cycles, primitive transport, and intense manual labor. The stone mass sat directly on foundation rock, where undetected seepage and inadequate drainage could build uplift pressure, threatening to destabilize the base. To handle monsoon floods without overtopping, Penneycook built 13 chute spillways, discharging up to 3,454 cubic meters per second, reaching the absolute limit of what manual stone laying could achieve. To conquer the Colorado River at Boulder Canyon, engineers abandoned stone for mass concrete. Under General Superintendent Frank T. Crow and the 6 companies consortium, workers first spent over a year blasting 4 diversion tunnels, each 56 feet in diameter, through sheer canyon walls. The work was hazardous, with miners facing intense heat, carbon monoxide, and falling rock, culminating in a brief strike in August 1931 over safety and living conditions. Once the river was bypassed, Crow coordinated a continuous 24-hour operation of rail-mounted cableways and concrete batching plants. Pouring Hoover Dam as a single block would have trapped the heat of curing cement, causing the structure to crack and take over a century to cool. To prevent this, Crow placed interlocking concrete blocks in 5-foot lifts. He ran 582 miles of steel pipe through the blocks, circulating water chilled by an on-site plant producing 1,000 tons of ice daily. This arch-gravity structure relies on a base thickness of 660 feet to resist water pressure, while its curved design transfers the load of the massive reservoir into the canyon walls. Following Hoover, Bureau of Reclamation Chief Designing Engineer John L. Savage scaled this approach to the Columbia Basin with the Grand Coulee Dam. Built between 1933 and 1942, Grand Coulee stands 168 meters high and spans 1,592 meters in length. Relying purely on gravitational mass rather than arch action, the structure required 12 million cubic yards of concrete. Savage designed the dam to power regional industry and irrigate hundreds of thousands of acres of farmland. The project initially generated nearly 2,000 megawatts, a system later expanded to 6,809 megawatts. Following World War II, governments transformed dams from isolated public works into instruments of national development. This global expansion relied on new funding networks, from World Bank loans to Cold War rivalries, exporting massive river interventions across continents. On the Zambezi River, the Kariba Dam was completed in 1959. Standing 128 meters high with a reservoir holding 180 cubic kilometers, it generated 1,626 megawatts, but forced the relocation of over 50,000 Tonga people. In Egypt, Soviet financing and engineering backed the Aswan High Dam, constructed between 1960 and 1970. Standing 111 meters high and 3,830 meters long, it impounded Lake Nasser to store 132 cubic kilometers of water and generate 2,100 megawatts. While regulating seasonal Nile floods, the project displaced local Nubian communities and altered sediment delivery, starving downstream agriculture of natural nutrients. In the United States, the Bureau of Reclamation built the 216-meter-high Glen Canyon Dam between 1956 and 1966. Its reservoir, Lake Powell, stored 33 cubic kilometers of water to generate 1,300 megawatts, but drew sharp public criticism from conservationists like David Brower. By trapping sand, silt, and gravel, the dam altered downstream water temperatures and seasonal flows, disrupting riparian ecosystems. Whether funded by the World Bank, the Volta River Authority, or superpower rivals, these massive barriers forced a fundamental question. Can an entire river system absorb the scale of human control? On October 9, 1963, the Vajont Dam in northern Italy faced a severe geological crisis. Designed as a concrete arch standing 262 meters tall, the structure remained intact when a landslide tore down the slopes of Monte Toc. An estimated 260 million cubic meters of rock plunged into the reservoir, displacing a wave of water that overtopped the crest by 250 meters, destroying several downstream villages. The official Italian Commission of Inquiry recorded 1,917 fatalities. Geologist Edoardo Semenza had previously warned that Monte Toc was unstable, identifying an ancient landslide mass that would shift when the reservoir filled. His warnings went unheeded, showing the limit of structural strength without slope stability analysis. On June 5, 1976, a different failure mechanism destroyed the Teton Dam in Idaho. Standing 93 meters high, this earth-fill structure breached during its initial filling, causing 11 documented deaths. Post-disaster investigations pointed to poor compaction and weak grout curtains. Water infiltrated the highly fractured volcanic foundation, triggering piping, a form of internal erosion where water carries soil particles through or beneath an embankment, progressively enlarging the path. These separate disasters, one a reservoir geology slope failure, the other an embankment seepage breach, redefined global oversight. Dam safety shifted from a one-time certificate to continuous monitoring. Today, safety protocols rely on embedded piezometers and seepage gauges to track water pressure, alongside deformation monitoring and probabilistic flood studies. Dam break modeling and emergency action plans prepare downstream communities, while independent technical reviews manage geological risks long after construction ends. In December 1994, Chinese water authorities and the China Three Gorges Corporation began constructing the largest concrete gravity dam in history. Spanning the Yangtze River, the Three Gorges Dam stands approximately 185 meters high and stretches 2,335 meters along its crest. Workers poured roughly 27 million cubic meters of concrete, managing the project in phases that culminated in full generator commissioning by 2012. Today, the dam's installed capacity of 22,500 megawatts is distinguished from actual generation, which varies based on water availability, grid demand, and strict reservoir operating rules. This massive barrier integrates flood regulation, navigation, and power generation, but at a profound cost. The rising reservoir forced the resettlement of over 1 million people, transforming local economies and cultural sites. It also created ongoing concerns involving sediment retention, altered downstream habitats, slope instability, and potential reservoir-induced seismic activity. To address these challenges, modern engineering relies on new materials and digital systems. Roller-compacted concrete, a dry concrete placed and compacted in layers by vibratory rollers, speeds construction while minimizing thermal cracking. This technique anchored the Grand Ethiopian Renaissance Dam on the Blue Nile. Rising 145 meters high, this gravity structure reached its maximum design storage of 74 billion cubic meters in 2026. While providing massive renewable energy, the project highlights the necessity of climate-adjusted flood analysis and ongoing transboundary water negotiations. To manage these assets, safety agencies deploy embedded sensors, automated deformation measurement, and satellite remote sensing data. But in some river basins, the modern choice is deconstruction. On the Klamath River, the selective removal of century-old dams represents a complex engineering task. Crews systematically dismantle concrete and earth barriers, routing millions of cubic meters of trapped sediment to restore salmon habitats while managing downstream infrastructure risk. Today, water management treats dams as active engineering systems, balancing ongoing storage against the lifetime of the river. Today, as shifting climates alter river hydrology, dams are no longer symbols of permanent conquest, but ongoing negotiations with nature. The question is no longer how we engineer these rivers, but how we manage the consequences. Share your perspective in the comments below.